Professor Adel needs no introduction. He's been with us سنين. But I take this year. Adel is.
So I'm switching to slides instead of writing on the board, but I'll go back to the whiteboard when it's necessary. Okay? Yes. Okay.
Okay.
So should we wait a minute or so?
No, you should start. There's only a couple of people.
Okay.
So you should start.
So I'm going to talk in this school about GR, which is really a mini introductory course on GR. The purpose of it is actually trying to gain the concepts. Why we need GR, why GR was such a natural product of the revolution which happens in physics in the early 20th century. Okay? So in order to do that properly, maybe it's important to go first very quickly over special relativity. Okay? Just to scan very quickly the concepts and the idea of special relativity. So let me start with that, but before that, let me just go over what are the topics that I'm going to cover, okay, in this mini course. The topics are going to be special relativity and the idea of space-time, equivalence principle, and why equivalence principle requires bending of light in a gravitational field, why we need tensors, and some tensor properties, tensor algebra, and the idea of covariant derivative. Then I'm going to talk about geodesic equations, but not today actually, maybe next time, and try to organize our thoughts a bit to try to figure out what are the field equations. Okay. Our first trial is going to fail, okay, which was like the simplest possible way of constructing the field equation. Then we try to understand more the setup that we have, and then we are going to introduce what is known as a curvature tensor, and from this we can actually reach Einstein's field equations. Then, contrary to what I used to do in this school, usually I jump from field equation and apply it directly to spherical solution, spherically symmetric solution, Schwarzschild solution. But this time I'm going to start with another application, which is cosmology. Why? Because actually we needed this in another course, and in fact it makes sense because it's simpler application to GR. Okay, it's a bit simpler than Schwarzschild solution. So I'm going to start with cosmology, driving Friedmann equations, and maybe applying it to a couple of certain cases like non-relativistic particles, or what we call dust, and radiation matter as well. Okay. Then we are going to discuss spherically symmetric solutions and the top equation. Maybe we'll go over this with some details or with some speed. I don't know. We'll see how it's going to take. Okay, so let me start with the foundations of special theory of relativity. So the special theory of relativity is based on two basic postulates or assumptions. First one is the constancy of the speed of light in vacuum in all inertia reference frames. Okay, this is the first assumption, which is actually was completely new, as they say, completely out of the blue. And the other one is kind of extension to Galilean relativity principle, which is saying that the laws of physics are the same in all inertia reference frames. So pretty much similar to the Galilean relativity principle. But the implications of these two assumptions was huge. First, the idea of absolute time, which we used to it in Newtonian mechanics, destroyed. Okay, we don't have absolute time anymore, and also we don't have the notion of absolute length or distance because of length contraction. Okay, and also we are going to talk a bit more about this, and as we all know, the equivalence between mass and energy. So let me start with the usual graph we used to it. Let's suppose that we have two inertia reference frames. That's to say the frames which move with respect to each other with a constant velocity, v. Okay? And let's try to figure out what was the relation between these two coordinate systems. Okay? Of course, in Galilean relativity, we know that this was given by a simple set of equations which were, anybody remember what was the set of equations we have in Galilean relativity? So we have t prime equal to t, absolute time, and x prime is actually x minus vt, and y prime is y, z prime is z. Okay? And simply, if we go back to this coordinate system, you can see that the difference between x and x prime is just this piece, which is really going to be vt. Okay? So this is simply the Galilean transformation. But what is the importance of the Galilean transformation? Why this is important? It's important because this collection of reference frames, which will vary this Galilean transformations, are the frames in which Newton's laws are valid. Away from these frames, Newton's laws are not valid. Okay? Simply because if you take these coordinates and take the derivative of it and the second derivative of it, you will get the same acceleration. Right? Because Vt term is going to disappear with the second derivative. So this ensures the forces seen by any of these inertial frames are the same. And there's no additional force will pop up to you in any one of them. But if you use non-inertial frames, you could have some additional forces, which we call fictitious or non-inertial or whatever, okay, force. So this is the importance of the Galilean transformation. So the idea was that Newton's laws and the whole setup of classical physics was actually invariant under Galilean transformation. But when Maxwell came up with his equations, and we know that these are laws of nature because of the several experiments has been confirming this in the late 19th century and in the early 20th centuries as well. There was a big conflict between them. There was a big conflict between this physical laws set by Maxwell's equations and these physical laws set by Newton, the classical mechanics. And the conflict was Maxwell's equations are not invariant under Galilean transformations. So what is going on here? And even Maxwell's equation, it has a velocity which we don't know, which is the speed of light. And we don't know what is this speed of light is reference to. We know that always velocities in classical mechanics, it's a relative concept, right? So when we say a velocity, we have to have a reference point to this, a reference frame to this, okay? So this C in Maxwell's equations is reference to what? Okay, so people thought in the beginning it is referred to what is known as ether. And then they said that this has to be the case, and this ether is the media in which the electromagnetic waves is propagating, exactly like when sound wave is propagating in air. And then Michelson and Morley experiment came, and we discovered that this is not true. Okay? There is no relative motion, okay, between, that's to say the measured speed of light was not c plus v or c minus v relative to this ether. It is again c, okay? Then we have a problem in physics. And this problem, of course, Lorentz tried to address it, and many great minds were trying to address it at the time. But the resolution to this problem came indeed from Einstein in his famous paper in 1905, okay, saying that this set of laws, which was Lorentz transformation, are going to replace the Galilean transformations, and this Lorentz transformation, we need to set it up in place of the Galilean transformation. That's to say, all physical laws that we are going to address has to be invariant under this laws of this transformation. And the reason for that is the constancy of the speed of light. The speed of light is constant in all inertia reference frames. Okay? So this is the transformation he reached, and the main idea of this transformation is to make actually the speed of light is the same in different reference frames. So if you take this quantity, which we call it the interval, okay, the space-time interval, for the case of light, it is 0, s squared here is 0, so you can see that the speed of light in the prime system is going to be c, and in the unprimed system is going to be c as well. Okay? Yes?
Lorentz transformation, Lorentz static. وأينشتاين static. بس كده. ليه الابلكيشن جاب من شغل أينشتاين والناس تانية فكرت ليه ما ناخدش الابلكيشنز من شغل لورنتز؟
Because right. Because first, الset of assumptions أي physical theory ماشي بتبقى مبنية كده زي piece of mathematics على certain assumption. فالعبقرية في رأيي يعني بتاعت أينشتاين إن هو بيحاول تدistinguish ما بين إيه هو إيه هي الفاكت اللي أنا مش هينفع أستخدمها. لورنتز مثلا ما تصورش إن constancy of the speed of light does no feature. ما تصورش ده. لأن كل الناس بتوع الكلاسيكال فيزيكس ما كانوش بيتصوروا. تمام؟ فكل ده ليه علاقة بالاورجنايزيشن بتاعت ايه الفاكتس المهمة او ايه الاسامبشن اللي انا ما اقدرش استخدمها.
يعني حط برنسبلز.
حط برنسبلز تمام وهو اهمهم ده الكونستانسي اوف ذا سبيد اوف لايت. الثاني اللي هو بتاع ان all physical laws are the same in all inertia reference frames. Actually he didn't come up with something new. It was the same as the Galilean.
لورنتز برضه ما شالش الايثر. يعني فضل معاه.
حاول يفسر لان هو كان عندهم مشكله. موضوع الايثر ده كان فيري امبورتنت لان عايزين يقولوا السي دي كانت ريليتيف تو ايه؟ فده كان ايثر فعملوا بقى ايدياز بقى عملوا complicated ideas على موضوع الايثر ده زي الدراج ايثر وحاجات
اينشتاين شالها خالص.
كل ده كان تحقيق في حاجات مالهاش لازمه بس الفكره بتاعت اينشتاين كانت روباست. كانت قويه جدا وفكت اللغز فعلا. فعشان كده حتى الناس لما قاموا في الاول بعد كده بعد النجاحات بتاعتها بالذات الديسكفري بتاع اللايف تايم بتاع الميلز وحاجات كتير جدا قبل كده كمان يعني فكت
just from السؤال من difference between both لورنس يعني يعني بس الموضوع الاول هو بيعمل مثلا تريك لورنس ترانسفورميشن على التايم just to keep maximum equations invariant at the mathematical trick ما لهاش اي ريزلت. لو تبص على اللورنس كونتراكشن زي ما قال كونتراكتد ريزلت كان بيفسرها على ان كانك ماشي كوره كده جيلي مثلا في جوه فهي ده الشيء بيحصل مثلا كده
لا يعني مش عايز اطول قوي في القصص دي لان في قصص كتير مرتبطه بالحاجات فخلينا بس نحاول نمشي على قد ما نقدر ببيس معقول. طيب الانترفال دوت تمام هنشوف بعد كده او اكشولي الانترفال دوت من الكوانتيتيز اللي هنشوف ان هي invariant in the sense that it doesn't change from an inertial reference frame to another. Okay? And in fact this interval dividing events لينا لان الانترفال ده هو actually difference ما بين two events they are happening in different times و different points in space. Okay? فالايفنتس ده ممكن الاس سكوير بتاعته تبقى time like which means it is negative لان النيجاتيف part more than the positive part. So this is time like and this is representing okay the difference between two events. Okay ممكن يبقوا different events لparticle with mass ماشي في السبيس وايفولفينج مع التايم. اوكي وممكن يبقى الاس سكوير ده زيرو و in this case as we said it is like this is called light like or non like. اوكي وده propagation بتاع اللايت من point ل another in space وممكن يبقى space like. اوكي وال3 دول ال3 possibilities we can actually draw them. It's better always to draw them in a geometric way. So if this is time and this is the position, we get something which is called the light cone. The light cone الانتيريور بتاعه اللي هو this part and this part is causally connected مع بعض. بمعنى ان اي events هنا حصل في الماضي تمام ممكن يكون الكوز بتاع ايفنت هنا في المستقبل. تمام انما ما ينفعش يبقى ايفنت هنا outside the light cone مأثر على ايفنتس في المستقبل. تمام بمعنى ان كل السبيس لايك انترفلز زي ده مثلا الايفنت ده والايفنت ده دي cannot be causally connected. تمام يعني ما ينفعش دوت يأثر على ده في المستقبل. اوكي ليه؟ عشان لو هيأثر عليه ده it requires ان هو يبقى عنده speed more than the speed of light وبالتالي ده طبعا حاجه unphysical فدي حاجه مش موجوده. عشان كده بنسمي اللايت كون ده الكوزوال كون. صحيح. اوكي this is the causal cone. اوكي introduction of Lorentz transformations which is these transformations okay خلتنا نحاول نخلي كل اللوز اوف فيزيكس اوكي look the same لما نروح من فريم لفريم. اوكي it means that they have to obey in a way or they have to transform in a way through this Lorentz transformation. فخليني تو يعني في حاجه تستنى ايه في سؤال هنا سوري مش رافع ايدي كفايه بس
ممكن السؤال اللي فات او لا هي بتاعت هو انا مش فاهمه ايه الفرق بين التايم لاين انترفل والنون لاين انترفل، يعني ايه الفرق بين التو ايفنتس كونكتد باي لايت راي هما كونكتد عشان يبقوا زي الفلوشن.
الفكره
Read what is on the slide.
يعني
Smaller than zero and bigger than zero.
يعني هي الايفنتس الفرق دي تمام، الكميه دي
Certain.
ليها 3 possibilities بس، لانها ميكس ما بين بوزيتيف ونيجاتيف، مش كده؟ ليها 3 possibilities بس، لا اما تبقى نيجاتيف يبقى النيجاتيف بارت دوميننت، تمام؟ In this case we call it time line، تمام؟ لا اما بتساوي زيرو لان التو بارتس كانسل each other، ماشي، ودي بنسميها نون لايك او لايك لايك، او تبقى بوزيتيف ان البوزيتيف بارت از دومينيتنج ودي بتبقى سبيس لايك، تمام؟
اللي انا اقصده ان هما وانس ان هما كونكتد باي لايت راي اكيد
مفيش، ده بس اللي كونكتد باي لايت،
Any
ده بس اللي كونكتد باي
definition
لايت.
is really, I mean, the point is it should be obvious. You shouldn't be asking this because the definition is CT. What is C? Speed of light. So this is the distance for light. If it's bigger, then it can make it compared to the distance between the coordinates, right?
اوكي اللي انا
بصي
I mean, يعني
لا بنحاول نقوله يعني ان خدي العلاقه دي تمام واعملي التالي، عندك سي سكوير هنا تمام، ممكن تخليها سي سكوير بلس اس سكوير، والناحيه الثانيه عندك اكس سكوير بلس واي سكوير بلس زي سكوير،
just make it x.
تمام؟
To be
just make it x square او length square، خليها length square، تمام؟ you can see هنا ان c ماشي ممكن تبقى اكبر، ماشي، الفيلوسيتي عموما اللي هي ممكن تبقى نخليها
اسمع
اكس، ممكن نقسم على في تي هنا، تمام؟ اوكي، ف you can see يعني you can play with the equation anyway، تمام؟ you can see and you can divide this into 3 cases. الكيس الفيلوسيتي فيها اللي هي السبيشال بارت ديفايدد على التايم ممكن تبقى اقل من السي،
يعني عندي دلتا تي اوف 10 دقايق وانا رايح بالعربيه، تايم لايك ولا سبيس لايك؟
well, I'm not really
رايح اسكندريه.
I'm not really asking about questions.
ما هي كده.
about equations sorry.
هو
الكويشن بتاعي ان في البوسيبيليتي الاولى انا قلت ان الايفنتس دول في كوزاليتي، البوسيبيليتي الثانيه قلت ان مفيش كوزاليتي،
تمام.
البوسيبيليتي اللي في النص
لا خلينا نفكر جيومتريكال احسن.
باللايت راي. في كوزاليتي بيني وبين اسكندريه في 10 دقايق بعربيه ولا مفيش؟ That's all.
يعني الاولى والثانيه ان في كوزاليتي.
لو انا رايح بعربيه في كوزاليتي بيني وبين اسكندريه في 10 دقايق ولا مفيش؟ او في 10 ثواني؟ في كوزاليتي؟ لكن لو كلمت في التليفون في
هي الفكره كلها ان
For God's sake يعني.
السبيد الريكوايرد، تمام، عشان تو كوميونيكيت، تمام، السبيد دي هتبقى هي هنا ايه، تمام، ليها علاقه، احنا هنا اكس وتي مش كده، فممكن تبقى الانفرس بتاع السلوب مثلا، ماشي، فواضح جدا ان السبيد دي لما بتبقى اقل من الواحد، عشان هنا السي بواحد في الجراف ده، السي هنا احنا حاطينها بواحد، فهتبقى اقل من الواحد، فتبقى انسايد اللايت كون ده، تمام، فاي حاجه انسايد اللايت كون دوت ماشي بنسميها كوزل لانها اقل من الواحد، اللي هي اقل من السبيد اوف لايت، ماشي، معناها ان الحاجات كان كوميونيكيت، مش احنا متفقين ان مفيش حاجه اسرع من السبيد اوف لايت؟
انا ممكن انا بس بسال ليه؟ لان انا هنا الديفينيشن بتاعي الكوزاليتي ديبندز اون ايه؟ ان التايم وصل لليميت.
لا سيبك من الديفينيشن بتاعك للكوزاليتي، هو في ديفينيشن للكوزاليتي، تمام؟ الديفينيشن بتاع الكوزاليتي ماشي عشان بس نتكلم بشكل واضح. دايما احنا كلنا بيبقى عندنا في حاجات لا اما مش فاهمينها كويس قوي، لا اما في ملخبطين فيها شويه، بس الديفينيشن بتاع الكوزاليتي بشكل عام، تمام، ان انا بقدر التو ايفنتس دول اوصل بيهم اوكي بسبيد مور ذان ذا سبيد اوف لايت ولا سبيد اقل او تساوي السبيد اوف لايت بس.
كويس. ايه بقى تفسيري للماي ثوتس توداي بتأثر على الماي ثوتس بكره؟
ايه تفسيرك لايه؟
افكاري النهارده بتأثر على افكاري بكره. ما في كوزاليتي في الموضوع.
تمام.
ايه تفسيري انا للكونسبت الكوزاليتي؟
ايه علاقه يعني ده هيمشي طبعا مع السبيد اوف لايت عادي جدا، لان افكاري تمام في الاخر دي ماده والماده بتعمل انتر اكشن والانتر اكشن في الاخر مش هيعمل اي حاجه مور ذان ذا سبيد اوف لايت، فده مش خارج اللي احنا بنقوله تمام. بس ده يعني اتس سايد توك ماشي، اتس سايد توك. اوكي مش عايزين نضيع وقت اكتر من كده في القصه دي، بس ممكن نتكلم فيها زي ما احنا عايزين بعد التوك. اوكي فبس مهم جدا ان احنا يبقى عندنا التقسيمه دي. الاهم بقى من التقسيمه دي فكره ان احنا يبقى عندنا لورنس ترانسفورميشنز والفيزيكال لوز اللي عندنا تمام بتتغير معاها in a well defined way. الفكره جايه منين؟ جايه من تاني من الجاليليان ترانسفورميشنز تمام اللي هي الترانسفورميشنز الكلاسيكال ميكانكس تمام invariant under its action رقم واحد. بس في حاجه ثانيه كمان الكلاسيكال ميكانكس invariant under its action. ايه هي؟ تعال نبص كده بشكل عام ل لو عندي نيوتنز لو of motion. Newton's law of motion, I can write it simply as m x vector double dot equals minus gradient of some potential. مش كده؟ Do we agree about this؟ تمام. احنا عارفين ان الايكويشن دي invariant under Galilean transformation in a sense ان الفورس هتبقى the same. تمام؟ بس ايه السيمتري الثانيه اللي الايكويشن دي invariant under؟ Can you tell me؟ ايه السيمتري؟ ايه السيمتري ترانسفورميشن اللي الايكويشن دي invariant under؟
جيج سيمتري.
ايه؟ جيج ده نيوتن سكند لو. ايه اللي دخل الجيج هنا؟ التايم ريفرسال. تمام ده كلام مظبوط، بس خلينا من التايم ريفرسال والتايم ترانسليشن والسبيس ترانسليشن دلوقتي خليهم على جنب. ايه السيمتري الثانيه؟ روتيشن. بالظبط هنا في روتيشن. الروتيشن دوت اللي بيقول لك ان الفيكتور لو انا هعمل فيكتور برايم تمام خليني اتعامل معاه كماتريكس كولوم ماتريكس عندي ار اكس تمام. لو انا عملت الترانسفورميشن دي ده فيكتور وده فيكتور تمام. اي فيكتور is going to لو انا عندي تو فيكتور ايكويشنز A بتساوي B تمام اقدر اكتبهم كماتريكس كولوم ماتريكس تمام واقول ان A بتساوي B. في النيو سيستم هيبقى A برايم و B برايم و I can show to you اذا كان ده invariant under rotation هيبقى عندي R A بتساوي R B وطبعا اضرب في R minus 1 انها always defined as a group تمام و to remove ده والاقي ان في invariance under rotation. يبقى اذا الكلاسيكال ميكانكس عندي كانت invariant under Galilean transformation و under rotation وده very important fact. ليه انا بقول ده؟ لان كمان اللوز اوف فيزيكس اللي انا هتكلم عنها هنا هتبقى invariant under حاجه very similar to rotation اللي هي لورنس ترانسفورميشن. لورنس ترانسفورميشن اللي انا اتكلمت عنها دي من شويه اللي هي دي تحديدا انا ممكن اكتبها ككولوم ماتريكس برضه. والترانسفورميشن ماتريكس دي اللي هي بسميها جاما هتبقى مضروبه في الاولد اكس. فانا عندي اكس بقى بالمعنى اللي هي 4 دايمنشن ممكن اسميها برايم لامدا ممكن اسميها نيو اكس نيو. This how the space and time transform under Lorentz transformation. اوكي؟ طيب زي ما كانت الكلاسيكال ميكانكس بتحافظ لي على حاجه مهمه جدا، بتحافظ لي على الايكويشنز بتاعتي are covariant in a sense under rotation او it has the same form under rotation. كان في كوانتيتي مهمه جدا بتحافظ عليها اللي هي ايه؟ اللينث بتاع اني فيكتور. مش كده؟ لو انا عندي اي فيكتور نسميه A برايم وكان هو بعمله ترانسفورميشن از R في A الاولد، تمام؟ الفيكتور ده اللينث بتاعه انا دايما بعرف اكتبه على انه A ترانسبوز A. ففي النيو سيستم بقدر اكتبه تبع الترانسفورميشن دي، اعمل ترانسبوز، تمام؟ هيبقى A ترانسبوز R ترانسبوز وبعدين هنا في عندي R وبعدين A. فده بيقول لي ان الترانسفورميشن اللي عندي دي لازم تطيع ان R ترانسبوز R، تمام، بيساوي ايدنتيتي عشان يبقى ده انفاريانت، تمام؟ النوع الترانسفورميشن ده دايما بنقول عليه روتيشن، اللي هو بيطيع الايدنتيتي ده بنقول عليه روتيشن، تمام؟ هنا عندي نفس القصه لان انا عندي لسه قايلين ان اكس برايم ميو مضروبه في اكس برايم نيو اللي هي الكونتراكشن ده، وخلي بالك هنا الريبيتد اندسيز ات مينز سميشن، تمام؟ دي الكونفنشن بتاعتنا هنا دايما هي سايلنت كونفنشن، بس ده اكن عندي هنا سميشن اوفر 0 1 2 3. اوكي؟ فدوت هو عباره اللي انا كتبته من شويه اللي هي ماينس سي تي برايم سكوير بلس اكس برايم سكوير. الكوانتيتي دي برضو انا اقدر اكتبها كده كانها ماتريكس، فهكتبها كماتريكس انها اكس برايم لامدا اكس. نعمل الترانسفورميشن، تمام، بتاعتها. بس خلي بالك بقى ان الكوانتيتي دي اتس بيتر ان احنا نكتبها ازاي، اللي هي الكوانتيتي بتاعت الكونتراكشن دي. I can write it as x transpose eta x, where eta دي is minus 1 plus 1 plus 1 plus 1 وهنا zeros وزيروز. ده المترك لانها هي مش بتحافظ على اللينث ان ذا ايكليديان سنس اللي هو اكس تربيع زائد واي تربيع زائد زد تربيع، لا، ما انا عندي فيه ماينس تي سكوير او ماينس سي تي سكوير. فالماينس دي جايه منين؟ جايه من الايتا دي، تمام؟ فلما نعمل الترانسفورميشن دي، تمام، بنلاقي برضو نفس القصه ان اكس ترانسبوز، تمام، لامدا ترانسبوز ايتا لامدا اكس بتساوي اكس ترانسبوز ايتا اكس. فده يقول لنا ان الترانسفورميشن دي لازم تقول لي ان لامدا ترانسبوز ايتا لامدا هي عباره عن ايتا، تمام؟ اكن الايتا دي زي الايدنتيتي عندي.
بس هنا هيكون روتيشن في الكومبلكس بلين.
بالظبط. انا actually ده this is true، ده روتيشن في الكومبلكس بلين، تمام؟ بس هي من وجهه نظري الجروب theory is the same، تمام؟ it's not that different، تمام؟ بس هي transformation in a way. okay؟ this is the important part انها transformation. فالفكره بقى ان الترانسفورميشن دي it acts like a rotation في الكلاسيكال ميكانكس. فانا عايز اللوز اوف فيزيكس اللي عندي تبقى covariant under this transformation، بمعنى ان شكلها ما بيتغيرش under this transformation. فعشان اكتبها لازم اكتبها زي ما كتبت الفيكتور بتاع الكلاسيكال ميكانكس، مش كده؟ ما انا كتبت الفيكتور ايكويشنز دي ليه كده؟ عشان تبقى invariant under الروتيشن دي. انا عايز برضو اعمل نفس الحكايه في الريلاتيفستيك ميكانكس، اكتب الايكويشنز كلها in the sense انها تبقى covariant under Lorentz transformation. فده it requires ان انا اعرف فيكتور جديد بقى، مش 3 dimension فيكتور but 4 dimension فيكتور. وده هو الاسنس بتاع ال 4 dimension فيكتورز اللي احنا اصلا ابتدينا بيه مع الاكس ميو، تمام؟ اللي هو ليه temporal ايكويشن، ليه temporal بارت وليه سبيشال بارت، تمام؟ وممكن اخد منه derivatives as well، تمام؟ يعني ممكن اعرف بدل النبله اوبريتور اللي هو فيه partial x partial y partial z بيبقى عندي كمان partial t، واكون منه اوبريتور ثانيه زي سكند اوردر اوبريتور زي partial mu partial nu اللي احنا بنسميه ده لامبرتشن اوبريتور، تمام؟ المهم بقى جدا ان انا تو ريكولكت الفيكتورز اللي عندي مع كوانتيتيز ثانيه اللي هي التمبورال بارت بقى عشان اعمل 4 فيكتور. في السبيس تايم I did already that، ان انا اخد السبيشال كوردينتس مع التايم. في المومنتا بعمل كده، يبقى عندي 3 سبيشال مومنتا مع الانرجي، بقدر اعمل 4 فيكتور، تمام؟ الفور فيكتور ده بكون منه quantities which are already covariant under Lorentz transformations، تمام؟ نفس الحكايه بالنسبه للويف نمبر اللي هو 3 كومبوننت مع الفريكونسي، بقدر اكون برضو منهم 4 فيكتور. نفس القصه مع الكرنت، عندي الكرنت دنسيتي مع الرو اللي هي الدنسيتي اتسلف، اوكي؟ اقدر اكون منهم 4 فيكتور. ببتدي ابص للفيزيكس in a completely different way، اوكي؟ as a collection of 4 things مش 3 things as we used to في ال classical mechanics او في الكلاسيكال ريلاتيف كلاسيكال فيزيكس يعني، تمام؟ طيب نيجي بقى للالكترومagnetism، ودي مجرد بس صياغه لانها مهمه بالنسبه لنا بعد كده عشان تفهمنا ازاي نمشي actually في ان احنا to find اينشتاين field equation. لان خلي بالنا ال only consistent theory, consistent field theory we have till now classically is Maxwell theory. Maxwell theory is the only consistent field theory that we have before of course general relativity. فهي كانت الجايد بتاعنا. فعشان الجايد دوت يبقى جايد effective وليه معنى I have to put it in a relativistic form عشان افهم where I'm going، تمام؟ فالفكره في الالكترومagnetism ان انا بقى كولكت تاني زي ما قلنا 3 components مع some component عشان اعمل الفور فيكتور. in this case هتبقى الفيكتور بوتنشال بتاع الماجنتيزم مع السكيلر بوتنشال بتاع الفاي بيعملوا لي 4 فيكتور، تمام؟ and this is not enough في الحقيقه ان انا اكون الاي ميو as a 4 فيكتور ان انا اعمل الالكتروداينامكس او الالكترومagnetism، لان الالكترومagnetism فيها سيمتريز ثانيه اللي هي الديجي سيمتري. فان اوردر تو دو ذات I have to construct a second order anti-symmetric او second rank anti-symmetric tensor اللي هو الاف ميو نيو اللي هو عباره عن السيمترايزيشن بتاع الديريفاتيف بتاع ال A ميو، يبقى partial ميو A ميو minus A نيو A ميو، تمام؟ فإن a sense relativity is telling us that an entity that you have which is physically meaningful is the strength tensor F mu nu, which is really the mix between electric field and magnetic field. So there is no meaning to a separate notion of electric field or magnetic field الواحد. They have to be combined in this entity which is called the stress or field stress tensor. Field strength tensor. Okay? In very similar way to the momentum and energy. There is no meaning to talk about separate momentum and separate energy. They are combined in a way because there are transformation laws which mix them, right? So you cannot really separate between P and E. The same way here, you cannot really separate between E and B. Okay? And using this variables, we can write down Maxwell's equation as a 2 simple equations. Okay, this equation, which contain Faraday's law and the divergence of B equals 0, and this equation which contains Gauss's law and Ampere's Maxwell law. To give you an example, how can you get something out of this equation? Let me choose this one. Okay, you can see here that this is the derivative of f mu nu. Okay, and here there is a repeated index mu and mu, so we have summation. Okay, and to the right hand side we have a current which is rho and j. Okay, so let us try to see how can I get anything from an equation like this, just as an exercise for you, how to deal with such notations and such equations. So let me just take this as an example. Okay, this is a repeated index, which means partial, but let me choose first. I'm going to choose, this is an anti-symmetric tensor, which means that there is no similar indices here. So if I choose nu to be the temporal, the 0, 1, mu could be 1, 2, or 3, right? The spatial ones. Okay? So 0, this is a placeholder for the temporal, okay, component. And if this is a temporal component, since this is skew symmetric, it means the only thing survive that these two are different. Okay? They cannot be the same, otherwise it would be 0. So I will have, if this is 0, is going to be 1, f1 0 plus 2, f2 0 plus 3, f3 0, and this is equal to mu naught j0. What is j0? It is c rho, right? j0 is 0 multiplied by mu naught. Okay? Now, if we go back to the component of the tensor itself, you will see that the 1, 0 components, okay, are this has to be the electric field, right? So I'm going to have partial I, EI, but we have C downstairs, and this is equal to mu naught C rho. And now I can multiply C here. And what is C squared? C squared is 1 over mu naught epsilon naught, right? So you can see that div E is equal to rho over epsilon naught. This is one of Maxwell's equations, okay? And the other equation you can get out of this equation is Ampere Maxwell equation, okay? But anyway, I will leave that as an exercise if you are interested. And this equation, you can get Faraday's law and div B equals 0 from it, okay? So this is an example on how we can manage this notation and understand it. Any questions so far? Yes?
Shouldn't we, before collecting terms and putting them in a full vector example, should we check first that they are a true chart representation of the full vector? I can't just collect four vectors and put them in a column and then just say they are full vector. I need to check that they are a true chart representation.
Of course you have to do that, okay? Any collection of 4 entities are not 4 vectors, okay? But any 4 vector has to be 3 components which act as 3 vectors in classical sense, okay? So the problem is to come up with a temporal equation always, and you need to make sure that the transformation of the temporal equation is going consistent with the other ones. Okay? But yes, you are right. We cannot choose any four component and say this is a four factor. Yes? If what? Negative what? Where? Here? This one? Okay. Yeah, I mean you can see because I might have used the different components for every unit, okay? Because I needed to have this picture, okay? So I might be off with a minus. Okay? So maybe this is switched. Here the minus sign and here is plus sign. Yes.
عشان نعمل construction بس الانرجي معلوماتها
I prefer to keep the discussion in English.
if we want to do stuff for vector for vectors, what are the conditions or restriction on the for vector will be
I just answered.
like there is a test.
You have at least the three components will be three components of the whole vector. Okay? And you need to make sure that the temporal component is transforming properly. Okay? So that only you have one problem with the temporal component. You need to make sure that it transforms properly. Okay. Now we come to a very important issue, which is try to prepare ourselves conceptually to the ideas of general relativity. Okay? So the main two ideas or the main two assumptions of general relativity are the following. First, the equivalence principle. Second, the general covariance principle. So the equivalence principle is saying that the inertial mass and the gravitational mass are always the same. Okay? I'm going to talk about this in more details later, but let me just state the principles. Okay? Or you cannot, in another way of saying it, you cannot really distinguish between a uniform gravitational field, okay, and a uniform accelerated field. Okay? You cannot distinguish physically between these two situations. For the general covariance principle, we are replacing, okay, Lorentz transformation of the special theory of relativity and the covariance of physics in different inertia reference frames by the covariance of physics in any reference frame. Okay? In any reference frame, so this is to say that we have arbitrary coordinate system. So we need to be able to transform the physics between any coordinate system and another coordinate system, even if it is non-inertial. Okay? So let's try to understand why we need these two assumptions. The first, which is the equivalence principle, let's first review very quickly what is the definition of inertial mass. Inertial mass is the mass, we write it in Newton's second law, which basically is the resistance of the object, okay, when we influence it by some force. Okay? The resistance which resists, okay, the object from motion. I mean, of course, this is hand wavy, but it is basically the resistance of acceleration. This is the inertial mass. And the gravitational mass, in fact, is the source or the response of the object to a gravitational field. Okay? You can think of it either the source of a gravitational field or also the response of the object to a gravitational field. This is the gravitational mass. And these are two different concepts, by the way. Logically, they are different. But it happens that they are exactly the same. There are several experiments, okay, in the late 19th century and early 20th century, which confirms that they are exactly the same. Till today, I think the bound is something like they are identical till 10 to the minus 13 or 10 to the minus 14. Okay? So they are very, very identical. So Einstein assumed that they are exactly the same. They are the same thing. Okay? But being the same thing is that if you equate these two equations, okay, of course, this is the general form of a force and this is a gravitational force. When you equate this and you equate mg with mi, you will get an acceleration which is Newton's constant times the mass of the big object divided by the distance squared. Meaning that...
You have another minus sign there.
Oh, yes. But when we write it like that,
Okay.
this is a magnitude.
I'll pass.
Yeah. Okay? So, what is the meaning of this? What is the meaning that the acceleration of the object does not depend on its mass? First of all, do we see this in other forces? Do we see this in other forces? Like electrostatic force or magnetostatic force? Any other force? No, you don't see this in other forces. Okay? Always the acceleration will depend on the properties. But here, the acceleration does not depend on the physical properties of the object. Meaning, instead of this, let's suppose that this is Earth and this is the Sun. Instead of this Earth, you will put an ant, you will put an elephant, you will put a pencil, whatever. As long as it starts from the same position and with the same velocity, you will end up having the same path. You will end up having the same orbit. Okay? This means actually, since this force does not depend on the property of the object, I can remove this concept of force and imagine that the space itself, okay, is causing these curves, okay, and the gravitational interaction is just a property of the space. So this big object is causing the space to bend in such a way to have all this object taking the same path or taking the same orbit or taking the same trajectory. Okay? This is the basic idea of general relativity. Because of the equivalence principle or because of the equality between the inertial mass and the gravitational mass, I can think of gravity in such a way as a geometric, okay, effect. Okay? So let's do more thought experiments. So I will do what is known as the elevator experiment. So let's assume that we have an observer inside an elevator without any window, and this observer cannot distinguish between two situations. Being in a uniformly accelerated rocket in deep space, like its rocket going up, or being at rest in a uniform gravitational field, very much like this picture. So we have a guy here on Earth, okay, and he's making an experiment with an apple, dropping it. You can think of him like Newton. And another guy in space going with some acceleration which is exactly equal to g, and again doing the same experiment and getting the same results exactly. Okay? Indeed, there is no physical experiment, okay, which involves gravity that can you think of which can distinguish between these two situations. Okay? Meaning that you can always mimic the gravitational field by an accelerated frame. Okay? This is one experiment. And there is another experiment, which I didn't put it here, okay, but I need to also talk about it quickly, is let's suppose that the same guy, okay, in the elevator, or the same two guys in the elevator, okay, one of them, which was Einstein in this case, and we are going to cut the rope. Okay? Now this guy is going to have a free fall. This is a free fall. This is a situation, and the other situation is we take Newton with his weight and set it with a constant velocity. Can you distinguish between these two situations?
Yes, Einstein will die.
He's already dead.
Newton is
By the way, you didn't know that. He's
No,
already
we
dead.
knew that.
So you cannot actually distinguish between these two situations. Okay? In other words, okay, you can remove the effect of gravity if you go to certain reference frames, which is a free-falling frame. So this is really a fictitious force, as Einstein once said. It's some sort of fictitious force. It's not non-inertial force like Coriolis or centripetal force. It's not, because there is still some physical difference. Okay? But it is, in a sense, a fake force or a very strange force. Yes?
Isn't that just a true statement of the Flatness theory? That
What
means
is the Flatness
any
theory?
is conformity
Yes.
to
This is a sophisticated way of saying that curvature, if you look at it very, very locally, you'll find that it's described by a flag. Yes?
Is that if the birds will be applied also if the acceleration is non-uniform for time variables?
What do you mean by that?
For example, the acceleration will change from position to position or from time to time.
If the elevator is very big,
Hmm?
if the elevator is very big, that's what you
For
mean.
example,
Oh,
Then you'll see
you're
tidal
saying
force.
globally, yes, locally change.
Right, but we avoid saying that because this is not really accurate. So the equivalence principle, okay, is accurate when we talk about it locally, not globally. Globally, you start to have some correction.
And that's why you
This is
see
exactly
curvature,
the
Adel.
Hmm?
That's why you see curvature.
Exactly.
That's why that's
But you see it on the second order,
yes.
as a second order effect. So the way is that we really can identify completely gravity as a curvature. Okay? But if you zoom in locally, you can in a way remove this
Like
effect.
flat, confident.
Yeah. And go with some accelerated frame and you see it as nothing. There is nothing. But this is like a first order effect. If you go to higher order corrections, okay, you will see still curvature components are there. Okay? So this is why I'm insisting to be local. Okay? So this is another experiment, and there is a third experiment, which is an interesting one. Let's suppose that we have a guy who is also accelerated with some acceleration equal to g up, but this time g is very high. Okay? Not as in our g on Earth, but this is very high g. And you can see that this observer will see that the ray of laser light, which is going from the left side of the elevator to the right side, is going to bend down. Okay? Of course, this is going to happen, okay, because of the dynamics. But remember, we said that this situation is equivalent of having a gravitational field, okay, on Earth. Okay, so this means that actually gravity is going to affect the trajectory of light. It's going to bend light. And this is where Einstein figured out how gravity is going to bend light. Okay, from the equivalence principle, because these two situations are equivalent. Okay, so you can see from these three experiments. Okay, now let's try to wrap up our thoughts.
I imagine what happened if equivalence principle is wrong.
But if the equivalence principle is wrong, it could be actually, it could be with some other interaction. So what we know it is the following, that the equivalence principle is correct to a very high degree. Okay? But we could imagine that at very, very high energy, for example, or very, very high curvature, that this might be not correct.
Black hole,
Okay.
for example.
No. I'm talking about effects which are with very high curvature and very high energy. Okay? High curvature, I think GR will still maintain.
Quantum gravity.
Hmm? Quantum gravity, for example. So this could be not enough to describe our world, but we don't know. But nobody is excluding that, by the way. Okay? Even there are some gravitational theories which include that. Okay? They don't insist on having equivalence principle.
We can say equivalence. Equivalence is basic.
For GR and for what we know, it is. It is very, very good approximation, and it could be the whole truth, and nothing but the truth. It could be. Okay, now let's try to wrap up our thoughts. So now we know that first, in order to describe gravity, we need curvature of the space-time, because light is bended. Okay, and light is our guidance in knowing actually what is the geometry of our surrounding world. Okay, so if light is bending, it could mean actually that the geometry around the massive object is indeed curved. Okay, and also from the concept itself that we explained in this experiment, that we can replace. There is a possibility that we replace gravity by curvature, space-time. It seems with all this thought that it's better to use curvature, or it's better to use curved four-dimensional space to describe gravity. Okay? And because of this problem, or because of this fact, that when we use different coordinate systems, we could have different results, or we could remove, okay, the effect of gravity a bit. Okay, we need also to be able to go from reference frames to another reference frames, and these are not inertial. Okay, so combining these thoughts together, you find out that we reach the two principles of general relativity. First, okay, of course, the equivalence principle, because we have no way of saying that it is wrong. It's experimentally actually valid and okay so far. Okay. Second, that we need a formulation of physics in such a way that we can actually describe physics or the physical laws in a covariant way in all reference frames, in all coordinate systems. Okay? So let's start with this, because this is the most sophisticated and important condition. If we are going to describe physics in a general covariant way, okay, that we don't care about the reference frame. How can we do that? In fact, geometry is going to help us in this perspective, because there are transformations which exactly doing that, which we call general coordinate transformation in geometry, specifically in Riemannian geometries and in other types of geometries. So if you have a system of coordinates, let's say in 4 dimensions, so have x0, x1, x2, x3, and you want to actually go to another system which is very complicated, okay? It's not as we did in special theory of relativity, but this transformation could be completely nonlinear, okay? Transformation. So what are the objects which preserve these types of symmetries, okay? Because I'm going to use these objects later on to construct physical equations, exactly like I did with Newton's law, okay? I used vectors to construct Newton's law or any other classical physical law because it keeps the physics covariant under rotation, which is our coordinate transformation there, okay? So these quantities which has a specific or a well-defined transformation properties under these general coordinate transformations are what we call tensors. So this is the importance of tensors, because if you want to describe your physics in a way which does not depend on the coordinate system, you need to use tensors, okay? Because you need to transform equations, and these equations will have the same form in different coordinate systems. So what are these tensors? So a tensor is a geometric object that transforms in a well-defined way under coordinate transformation. And by well-defined way, we are going to explain what we mean by well-defined way. So we have a scalar, which is what we call a zero tensor. Like 5 minutes?
Yeah, you were interrupted quite a bit, so I guess
Yeah.
5, 10.
Okay.
Plus,
I don't think I will need more than that. Okay? So a scalar which is what we call 0, 0. 0 here for the number of indices which are contravariant, like up. And the other 0 here, the number of indices which is down. So you can see here, this is a rank 1, 0 tensor, which is a contravariant vector. It means it has 1 indices up and 0 indices down. And here it has 0 indices up and 1 indices down. And these are its transformation laws. Be careful here that these are not the same, because the new component is written as the derivative of x prime with respect to x, but here the components here is netting at the x derivative with respect to x prime, okay? So this is a big difference between the two. And for a general rank tensor, which has k indices up and l indices down, this is a transformation law. And the convention is, since our tensor, this is the new tensor in the prime coordinate, when you have indices up, you write the x prime up. And when you have the indices down, you write the x prime down. And then you fill out with any indices you want, because they are going to be contracted with this one. Okay? So this is the way to keep track of this. But what are the properties of these tensors? One of the nice properties, if you contract two vectors, one covariant and one contravariant, the transformation laws, okay, you can see here that this is mu and this is mu. And a repeated index means that we can use the chain rule, okay? And the chain rule, it means partial x alpha is going to be by partial x beta. And partial x alpha by partial x beta, you know that this is a chronicle delta, right? Do you know what is the chronicle delta? If alpha and beta are the same, this is 1. If alpha or beta are different, this is 0. It's very simple. Okay? Now we also have symmetric and anti-symmetric tensors in terms of if you swipe the indices. Okay? And this is very important because if you multiply two tensors with different symmetries, like one is symmetric and one anti-symmetric, and you contract them, this is 0. You can show actually that this is always 0. And it's very important exercise to do. So if I have A and B, one of them is anti-symmetric and the other one is symmetric, and you contract them, okay, this is always 0. And of course you can decompose any tensor to its symmetric and anti-symmetric part with this simple algebraic manipulation. Okay? Now we come to a very important concept, which is the metric tensor. So the metric tensor is a generalization of our simple metric in Euclidean geometry. Okay? So remember, in Euclidean geometry, if this is x and this is y and this is z, okay, and we have infinitesimal distance here along the x and infinitesimal distance here along the y, okay, this infinitesimal distance, or let me do it in another way, and this infinitesimal distance here, this is, let's say, dy, and this is dx. Okay, so you can see that this infinitesimal distance here, if I'm going to call it dl, so we know that dl square is dx square plus dy square. But if you go up, okay, in the z direction and you have dz, then away from the origin, okay, this whole distance, now let me call it ds square. So ds square is going to be dl square plus dz square. That's to say, ds square is dx square plus dy square plus dz square. Do you agree with that? This is a simple manipulation. We apply Pythagoras theorem twice. That's it. Okay? So this is the metric in the Euclidean space, in flat space. You can see that the notion of a distance between these 2 points, the origin here and this point, okay, is simply given by this infinitesimal. Okay? The general form of writing a metric is this form. So ds square is not just dx mu contracted, but we have components. Why? Because you know that if I didn't work in Cartesian, I work in spherical polar coordinates. Do you know how this is going to change? You know, this is simply going to be ds square equal to dr square plus r square d theta square plus r squared sine square theta d phi squared, right? So you can see here the components I have, even in flat space, is not ones or zeros. Like here, I have here 1, I have here r squared, I have here even r squared sine theta squared. Okay? So this is the most general form, okay, of the metric. The metric, which is the quantity through which I can specify the space-time interval, to calculate the space-time interval. If you think of it in Euclidean space, it is the distance, basically. But in 4 dimension, it's not distance only, because we know that time involved, so this is why we call it interval. Okay? And the metric has a very important role in general relativity. It is our potential. Okay? Like in electromagnetism, A mu is the potential, right? The phi component, the vector component, and these are the main players in the theory through which you can get everything. The same thing here. The metric is the most important quantity in our space-time description, because through which you can, by its derivative, you can get connection, and you can get curvature, you can get everything you need. Okay? And also you can use it to raise and lower indices. This is a very important usage of the metric also, because the connection between contravariant and covariant vectors are through this quantity which is called metric. Okay? And do I have time to talk about covariant derivative, or should I leave it to next time?
You can briefly,
Okay.
that was mentioned in the context also.
Okay, I have 2 slides only actually.
Yeah.
Okay. So now we come to a very important part, which is if I want to actually write down tensor equations, I need sometimes to take a derivative of something. Like when we did in classical mechanics, we take the nabla affecting the phi. Okay, so this is the first derivative with respect to phi. But you can see that the result was a vector, right? And even if you have a mu, or a as a vector, if you take nabla affecting a vector, you will get also, okay, a vector by a cross product, for example. Okay, or you can get a scalar by a dot product. So we need to make sure that when we take a derivative to a tensor, the resulting, okay, entity is transforming as a tensor. With higher rank, with lower rank, it doesn't matter, but it should be transforming as a tensor. So we need to make sure of that. This is easy for a scalar field or for a scalar quantity. If you take the derivative for a scalar quantity, it's automatically transforming as a vector. Okay? But when you do that with a vector, you will get a nasty second order derivative term. And this term is preventing us from having a tensor for the derivation of this vector. Okay? So what we should do with that? In fact, there is a whole setup, okay, to actually try to change the derivative, okay, by adding a term which is called the connection, and from this connection we actually make sure that this is transforming, the result is transforming as a tensor. But let me try to explain this in a more intuitive way, which is related really to the geometry. There is another way of discussing geometric objects, which is as index-free objects, okay? Like if I have a vector, I can write down the vector as a component and times a basis, not as a component as I did before, okay? In this way, I am confident that when I transform this, it's going to transform as a scalar at the end, okay? But this is what we call the geometric, okay, entity of a vector. So let's try to change this, okay? So if we change this vector, I'm going to change the component, and I'm going also to change the basis, okay? But somebody might actually look at me saying, how come the basis could change? When I have a Cartesian coordinate like that, and I have Ex here, Ey, Ez. These vectors does not change if I change the vector. That's true, because this is the simplest possible coordinate system. This is a very deceiving coordinate system. Think of the spherical polar again. You have ER, E theta, E phi, and change a bit the direction of R vector, and you will see that ER changes, E theta changes, E phi changes. So indeed, when you change the vector in general for arbitrary coordinate system, these bases are going to change. Okay? This is why this is a true in general fact. Okay? So when we do this, it's important to know how to deal with the change in basis. But the change in basis, if I take the derivative with respect to some coordinates, the derivative of a vector, it should be, or the derivative of a basis vector, it should be at the end a vector, right? And I can think of it like you specify a specific number for mu and nu, okay? Take mu, for example, to be 1 and take mu to be 2, okay? Now you have a vector which is, you can always write in terms of the basis. This is the fact, okay? So mu and u fixed, and you will write it as an expansion of a vector, like you write any vector in terms of a basis, right? So these coefficients, gamma, is what we call the Christoffel symbols, or the connections, which help us to fix this problem, okay? So if we take the derivative with respect to this v as a whole, we have two variations. The variation of the component v mu itself, which is this one, and the component related to the basis, okay, which I can write it like this, and you can see that this is again chronicle delta, so you can write this derivative as a partial v by partial x, okay, gamma v. And I'm going to interpret this as a new type of derivative, which is what defines for me the covariant derivative for this arbitrary curved space, okay? So this is very important because it keeps the properties of the tensor, okay? So whatever number of derivatives that I'm going to take later on, as long as I'm keeping this gamma there, okay, I'm going to end up with tensor. I'm going to stop here and continue next time.
Thank you, Ad. Any more questions?
Okay.
I don't see the motivation in interpreting gravity as a theory of curvature from the fact that the inertial mass and gravitational mass are equivalent. I know that historically the first attempt to construct a covariant theory of gravity was by attempting to construct the Poisson equation as an automatic equation, but obviously if you try to do this in 3 dimensions, all the connection coefficients will vanish. So this first attempt would not be very feasible. However,
But this, I think you are talking about the trials of Einstein in 1917.
this first attempt of two was attempted by Poisson before by Poincaré
Poincaré, oh, okay. Yeah, yeah, yeah. Okay.
So this motivates it more. If it resembles an autopilot equation, then
Why would the current?
because an autopilot equation is in terms of Christoffel symbols, symbols are a derivative of the vector. So if you can write down an analogy in terms of the gravitational potential, then you can interpret gravity as interpret the metric as a gravitational potential. But if you don't have this analogy, how do you interpret the metric as a gravitational potential?
But the metric is already, you can think of it as a gravitational potential,
What?
because the Einstein field equation is a second order, and I can think of even the geodesic equation as a force law. So
Yes, but it doesn't follow from any of the assumptions or the axioms being the equivalence of gravity and acceleration or the equivalence of inertial acceleration. This itself does not motivate the fact that we think of the metric as a gravitational potential. When we get these equations and then compare the autopilot equation to Poisson equation and realize that well, it resembles the 0-0 component of the Ricci tensor, then you can interpret it. You can interpret some sort of an analogy between gravity and acceleration without having this analogy, just having the equivalence of
but
gravitational mass.
why you are insisting of having the same form exactly as classical design? We could have different forms. I mean, I think you are.
Whatever covariant theory of gravity that you're trying to construct, it has to converge to Poisson equation at the weak level because Poisson equation works at the weak level. So
But you are
you want it does because first of all, he imposed this in the method of infinity. Even why do we borrow Newton concept? Why do we interpret the metric as a gravitational potential?
Why we interpret the metric as a gravitational potential? Because of this limit. You said.
Exactly because of what you're saying.
Yes,
In the weak field limit,
Yeah.
and
you
having
need to get-
trying to
you need
derive
to get
the
the
Poisson
critical
equation
gravity.
from GR. This
I'm
is
not
how it
sure
is.
to that. What I'm saying is having two axioms only being the equivalence of gravitational mass and inertial mass, and the other equivalence between gravity and acceleration does not give me a motivation to find the
What about
equivalence
the
between
general-
No, it comes in the weak field, and maybe Alexei will talk a bit about the potentials and perturbation, because maybe it will become clear when he talks about actually something similar to the weak range linear
I
perturbation theory. You will have gravitational potentials coming out in the metric explicit.
I do see this
You
analogy
do
from
that.
the field equations.
You will do that.
I can see the analogy from the
Patience.
I can see the analogy from the field equation. That's not my problem. But
So what's your problem?
in the first initial assumptions being again the equivalence between gravitational mass and inertial mass and the equivalence between gravity and acceleration does not give me a proper motivation. Those two assumptions themselves don't give me a proper motivation to think about the metric as a gravitational potential.
No, they don't. In principle, I guess they don't, but they are experimental facts that you see. And it turns out, let's say, you agree? Turns out. Alexei agrees, turns out. Everybody agrees. It turns out that the metric can be interpreted as a gravitational potential.
I'm not looking into this.
Right?
Why no?
No, a priori you wouldn't know. You wouldn't know that a priori.
It's not even that. I mean, if you can use these two principles and you can get infinite number of field equations. For example, in the case of f of r, you can have many field equations. So these are not very constraining assumptions, if this is what you want to say. These are not very constraining assumptions. But they are constraining in the sense that we have to geometrize gravity. Okay? But we need to move to other questions. And
Yeah,
maybe
it's
we
not
can-
unique.
Maybe we can continue the discussion when we have our break. Yes.
Is this condition term like interaction term like Lagrangian?
This is actually quite interesting because when we going to talk about geodesic equations, this term is going to actually collect for non-inertial forces
Like
gravity.
interaction.
No, not interaction. This could be fictitious forces which appear in non-inertial forces. Okay? Coherence forces, centrifugal forces, okay, will be connected in this graph. Okay? So it's a way to compensate the physics by collecting the other forces
Like
in the
quantum field, we try to predict the Lagrangian invariant, we add the interaction.
It is similar. It is similar to that. But here have even more physics. Okay? Yeah. Any other questions, guys?